Okay, we're going to start our review of this unit by looking at the different types of energies. So we started off with potential and kinetic energies, and we refer to these as being our mechanical energies. And these are the two that we're going to focus on in our physics class. We also are going to care about thermal energy, which can be referred to as internal energy or heat. There are other kinds of energies. This is not a comprehensive list, but examples are sound energy, light energy, and chemical energy. Sound energy is vibration of particles, so really it's a kind of kinetic energy on a microscopic scale. Light energy comes in many forms, like radio waves, infrared radiation, UV radiation, and lots of different kinds of light based on its frequency. We also have chemical energy, which is energy stored in chemical bonds. So anytime you have an exothermic reaction, that energy was stored in chemical bonds. We can also think about energy stored in like the cells of plants and animals, or the energy stored in the cells of a battery. But our focus again is going to be up here. We're not going to really care too much about these kinds of energies. We care about mechanical energy, and sometimes that energy can be converted into thermal energy through friction, for example. There are two kinds of potential energy. There's gravitational potential energy, which is based on an object's height, and there's elastic potential energy, which is based on an object's, or is the energy stored in a stretchy material like a rubber band or a spring. So we're going to be focusing on springs when it comes to elastic potential energy. Some examples of energy can be shown here in this Phet simulation, which I'll link to in this video. So here we're going to see the conversion of energy from one form into many others. So we're going to start here with the girl. She doesn't have much energy right now. We're going to feed her, so we're going to give her some chemical energy shown in green here. And now she can start pedaling the bike, so she's converting her chemical energy into a kinetic energy, rotational kinetic energy. The generator then takes that rotational kinetic energy and converts it into electrical energy shown in blue. That electrical energy causes the filament in the light bulb to get really hot, so it turns into thermal energy. And then once it gets hot enough, it begins to glow and it can emit light. And once she runs out of energy, the light bulb will eventually turn off. We can switch light bulb for another demonstration of conservation of energy. For example, I can have here some water that has already some thermal energy. We can give the girl some more chemical energy in the form of food. She can then convert that into kinetic energy again, which gets converted into electrical energy, which heats up this element here, which transfers thermal energy to the water. And once she runs out of energy, she can no longer pedal the bicycle. Here, the thermal energy is transferred to the water, eventually causing it to boil, and a lot of thermal energy is carried away with the steam. We can switch this generator for a solar panel. Although we need to change our source of energy, we can now use the sun as a source of energy, where it's going to emit lots of light energy. The solar panel converts it into electrical energy, which can then be used to heat up the water again, or to spin this fan, for example, using this electric motor. We should also see that some heat is being generated here by the motor, or maybe it's not in the simulation. Let me go back to the light bulb. So the electrical energy goes to the filament and it turns it into thermal energy. And to get an idea of what thermal energy is, we can look at this simulation, where in this box right now we have a vacuum, but we can fill it up with gas particles like this. And if we were to look at a gas on a microscopic scale, we would notice the particles of the gas constantly moving around, since they all have kinetic energy really. But on a macroscopic scale, we interpret that as thermal energy. So if I were to remove thermal energy from this sample of gas, I would notice that the particles would be moving slower. if I add thermal energy to the gas, I should notice that the particles are moving faster and faster. So thermal energy is really just kinetic energy on a microscopic scale. It's the kinetic energy of the individual particles in this gas. And we can use this third simulation to show kinetic and potential energy. So I have this dog here, and above his head will be a little circle to represent the total energy and the kind of energy that he has. So the blue represents potential energy here based on this legend, and green is kinetic energy. We can also see what kind of energy he has based on this bar graph here. So the higher up the dog goes, the more potential he has. And when I release the dog, it's going to change the potential into kinetic as he falls. We can do this again in slow motion. And as the dog falls, he gains speed, but it loses height. And so that's an example of conservation of energy there. We lose potential, but we're gaining kinetic. I can also put the dog on this ramp here, and I'm going to release him when he jumps off the ramp here, because I need to choose this option here where he sticks to the track. And now we can see if I release him, the energy will constantly change from potential to kinetic. No energy is lost to heat here because there's no friction in the simulation. But I can turn on friction here, and now the dog will begin to slow down because energy is being converted from kinetic to thermal energy. Eventually the dog will come to a stop here. So that was just a demonstration of some different kinds of energies. We can now go on to work, and work is defined as force times displacement. If a force is applied over some displacement, then work is being done. And when work is done on an object, it will result in a change in the energy of the object. So for example, we can have a change of potential energy, kinetic energy, or thermal energy. The units for work are newtons times meters, which are abbreviated to joules. The full equation for work is really work equals force times displacement times cosine theta, because the force and displacement both have to be in the same direction, and the cosine theta here takes that into account. So we can show some examples of work causing a change in energy. For example, if I have here a box and I apply a force on it in this direction, that force, for example, would be equal to the object's weight, and I apply that force over some distance d, causing the box to go to a higher elevation like this. The work done here results in a change in the object's potential energy. So the box here starts with 0 potential energy of 0 joules, and when the box is up here, it's going to have some potential energy, maybe 5 joules of potential energy. Yeah, so this is the initial potential, this is the final potential energy. Another example of work being done would be if we had that same box on a frictionless surface. This time we applied the force horizontally, and so the box does not gain any height, so it does not gain any potential. Instead, the box would gain kinetic energy. So after pushing the box some distance d, when the box gets here, it will be moving faster. And so maybe the kinetic energy started off with was 0 joules, and here now the kinetic energy is 5 joules. And so there was a change in kinetic energy in this example. One last example could be if we had a spring like this, and then we apply a force on this spring, causing it to become compressed like this. So we are applying a force like this on the spring. The spring was compressed some distance d, and so we started off with 0 elastic potential energy, and now we have some elastic potential energy stored in the spring here. So in these 3 cases, work was being done to change the energy of the object. Okay, so let's look at this example. Blocks A and B both weigh 600 newtons. Block A will be pushed up the frictionless 30-degree incline, so block A is going to follow this path. And block B will be lifted straight up, so block B is going to follow this path. In which case does lifting the block up to this platform require more energy? So we can use the equation work equals force times displacement for both of them. In this case, for block B, work for block B is going to be equal to the force times displacement. The force required to lift block B here is going to be equal to its weight. So the applied force here is going to be equal to the weight of block B. Block B's weight is 600 newtons. And so the applied force is going to be 600 newtons. We apply that force over a displacement of 2 meters. And so the work done to lift up block B is going to be equal to 1200 joules. And in this case, the force is pointing upwards and the displacement is upwards, so the angle between them is going to be 0. For block A, the force has to be applied in this direction, and the displacement is also going to be in this direction. And so the angle between these two vectors is still going to be 0. The force that has to be applied here is going to be equal to the force down the incline, so Fg parallel, and that's going to be equal to mg sine theta, so 600 newtons times sine 30 degrees, and that's going to be equal to 300 newtons. So we have to apply a 300 newton force. The displacement here, because of this 30-degree angle, is going to be twice the displacement here. So this displacement is going to be equal to 4 meters. And when we do that math, we get 300 newtons times 4 meters, and we also get 1200 joules here. So the work done in lifting block B is equal to the same work in pushing block A up this ramp. And we can predict that they're the same because they both end up with the same change in height, and so they both have the same change in potential energy. The change in potential energy for both of them is going to be equal to the work done. So they both have a change in potential energy of 1200 joules, and this is gravitational potential energy. So a similar question would be, I have the 2 blocks at the top of the platform, but now both blocks are allowed to slide or move downwards. Block A slides down the frictionless ramp this way and ends up here, and block B falls straight down. So we have it start here and fall straight down to here. And so it's moving straight downwards. Which has a higher speed when it reaches the ground, and which one gets to the ground first? Well, again, they both experience the same change in potential energy, and so they're going to both have the same amount of kinetic energy at the bottom, which means that they both have the same speed. Which one gets to the ground first? Because block B is going to have a larger force in this direction, force of gravity, which is equal to 600 newtons, and block A has a smaller force, it's the force of gravity parallel, that's only equal to 300 newtons. Block B is going to have a higher acceleration. Block B also only has to travel a short distance. Block A has to travel a long distance. And that means that block B is going to reach the ground first. And we can show that in our Phet simulation. Here. So I can have the girl start at this height and go down the ramp. And we can keep track of her velocity using the speedometer. So let's see how fast she's moving at the end. I can slow this down a bit so we can see. And when she reaches the bottom here, she's moving at about 9 meters per second. But if we let her go down the steeper ramp, when she gets to the bottom, she'll also be moving around 9 meters per second. We can also just have her fall straight down from this elevation, and she will still reach a velocity of about 9 meters per second. So because she has the same change in potential energy, she's going to end up with the same kinetic energy whether she's here, here, or here. And I'll play this at normal speed just so we can see that moving down this steep ramp, she gets down very quickly, but moving down the shallow ramp, it takes her much longer to get to the bottom. Okay, so now we're going to look at the equations for gravitational and elastic potential energies. So for gravitational, we need to, we're going to do work on this object. We're going to apply a force. The applied force here is going to be equal to the weight, which is mg. And if we move this up at a constant speed, such that all the work done is just equal to the potential energy. The object reaches some elevation here, and the force is still going to be m times g, and the displacement of this box is going to be the change in height. So the work done is going to be equal to the change in potential energy. So the work done is equal to the force times displacement. So the work done is equal to m times g is the force, and the displacement we refer to as delta h. And so we get the equation mg delta h, and this is equal to the change in potential energy. So this is our equation for gravitational potential energy. For the spring, in order to store energy in the spring, we have to apply a force, and we're going to apply that force horizontally. And as we compress the spring, the force on the spring is going to increase. So we start here with a force equal to 0 newtons. When we're here, we're going to have a larger force, which is going to be equal to k delta x. And when we're here, the force is going to be even larger. Again, k delta x. The change in length here is smaller than the change in length here. So as we continue to compress the spring, the force required is going to increase. So we really just care about the initial and final conditions, so we don't care about this intermediary step. I just wanted to show that the force is increasing. This change in length for the spring is our delta x value. And so now we can look at the work done on the spring. The work done is equal to force times displacement. Though here we cannot just use the final force here because it's not constant. And so we have to use the average force. If the initial force is 0 and the final force is k delta x, then the average force is going to be k delta x divided by 2. And then we multiply by the displacement delta x, and we get the equation 1/2 k delta x squared. And that's going to be equal to the change in elastic potential energy. Another way to look at this is by graphing the force versus displacement for both of them. So the force here for the gravitational potential energy, that's equal to m times g, and the displacement we refer to as h. And because here the force is constant, I can just draw a horizontal line to represent the force. On the spring side, the force is k delta x, and the displacement is delta x. But here it's not a constant force. It starts at 0 and it goes up to that maximum value k delta x here. And the compression is equal to delta x. So the work here is going to be equal to the area of this graph, and that's going to be equal to the change in energy. So the change in energy here, the change in potential energy, is equal to the height times the base of this rectangle, and we get mgh. Here, the work done is going to be equal to the area of this triangle, and the change in elastic potential energy is going to be equal to the area of this triangle, which is going to be 1/2 k delta x squared. We can now derive the equation for kinetic energy, though this is really optional. The equation here is 1/2 mv squared. So if you're a bit short on time, you can kind of skip this. I'll even write here, this is optional. So what's happening here is I have an object with an initial velocity vi. We apply a force to it, a constant force over a displacement d, and we end up with a higher final velocity. So to derive this equation, we're going to use our fourth equation from kinematics, where it's vf squared is equal to vi squared plus 2ad. We're going to isolate our 2ad, and that's going to be equal to vf squared minus vi squared. We're going to divide both sides by 2. So we end up with, let's also multiply both sides by m, because m times a is going to give us the net force acting on the object. So multiply both sides by m. And now we end up with the equation ma times d is equal to mv squared over 2 minus mv initial squared over 2. M times a we said is net force. So we end up with net force times displacement is equal to, I can rewrite this as 1/2 mv final squared. This is here is the equation for kinetic energy. But this is the final kinetic energy, and the initial kinetic energy was 1/2 mv initial squared. So we can see that net force times displacement, that's the net work done on the object. And here we have the final kinetic energy minus the initial kinetic energy. And this gives us the equation, I'll write it up here. Net work is equal to final kinetic energy minus initial kinetic energy is the change in kinetic energy. This equation is actually called the work energy theorem, which can come in handy sometimes. It tells us that if the net work on an object is 0, then we should expect 0 change in kinetic energy. An example of that is whenever we're lifting an object straight upwards, we might think, well, why doesn't the kinetic energy increase if I'm applying a force here? Well, so long as the applied force upwards is equal to the force of gravity, then you can see that the net force here is equal to 0 newtons. And so there is no increase in speed, no increase or decrease in speed for the object. All the energy, all the work done here just turns into potential energy. So here are our equations for gravitational potential, elastic potential, and kinetic energies. We also have Q. I should also add here the equation for work, which is equal to Ft cosine theta. So in most cases, we won't have to worry about this cosine theta. And this brings us to now the conservation of energy equation. This simply states that all the energy that we start off with in a problem is going to be equal to the final energy. And we're going to be using our these types of energies that we have here. So we're going to start off with our potential energy, gravitational, plus elastic potential energy, and kinetic energy. And our final condition will also involve the same kinds of energies: gravitational, elastic, and kinetic. And sometimes if there's friction, some of the energy turns into heat. So we're going to have this Q variable there. These are our initial values, and these will be all our final values. So we're going to be using this equation a lot. And then finally we get to power. The definition of power is pretty straightforward. It is a rate, and it is the rate at which work is done. And the equation is going to be equal to work divided by time, which can be rewritten as, well, work is force times displacement and divided by time. And then if I divide distance divided by time, I get average speed. So here are the different forms of the power equation. The units for power based on work over time are going to be joules per second. And the abbreviation for that is watts. So we can do a quick example here to demonstrate power. We have two elevators, both weighing 2,000 newtons, and they're being pulled up by two different motors. Motor number 1 lifts up the elevator in 20 seconds. Motor number 2 lifts up the elevator in 60 seconds. And so we can ask ourselves which of these two motors is more powerful. So to determine that, we're going to use the power equation, which is we know the force applied, which is going to be 2,000 newtons. We know the distance is 60 meters, and we have the time here for each motor. So the power rating for motor number 1 is going to be equal to Fd over T, which means the power rating is going to be equal to 2,000 newtons times 60 meters divided by 20 seconds. So the power rating for motor number 1 is equal to 2000 times 16 divided by 20. And we get 6,000 watts. The power rating for motor number two is very similar, FD over T. That's going to be 2,000 newtons times 60 meters over 60 seconds. So it takes, the numerator is the same. They both motors do the same amount of work, but motor number two takes much longer. It takes 60 seconds instead of 20 seconds. So since it takes 3 times as long, it's going to be outputting 3 times less power. So the answer is going to be 2,000 watts. And those are all the equations and concepts we need for the unit on work, energy, and power. And in the next video, we'll do some